Okay, friends, I welcome you all to our online C class. Good morning to all of you. And today's our lecture is Insertion Sort. In the last classes, we have discussed bubble sort, and then we have gone through the selection sort, and this is the third type of the sorting technique that we are going to discuss in today's class. So today's class lecture is moving like this. First we are going to discuss insertion sorting technique, and then we are going to evaluate the time complexity and space complexity, means the efficiency or you can say performance of insertion sort. And then we try to discuss one example how this insertion sort is done internally with a set of values we will take, and we will discuss the pass by pass how the status of the values will be after each pass. That we will see as a first topic, and then after that, once you are familiar with the procedure, then we are trying to develop pseudocode for this insertion sort. And then once the pseudocode is ready, using that you can write the algorithm, and writing algorithm is left as an exercise to you. And using pseudocode, I convert all pseudocode statements into C language function statements. And once function is ready for insertion sort, then we will write a complete program for sorting a set of integer values using insertion sort technique. And then related to today's class, some of the important questions which were covered in the previous examinations, which were asked in the previous examination, and then assignment questions related to today's class will be given to you. So let us start our discussion with insertion sort technique. Insertion sort is the technique which is widely used by the programmers, because compared with the bubble sort and selection sort, the number of comparisons in the insertion sort is less. So therefore, it gives better efficiency than the selection sort. Selection sort is better than the bubble sort, and insertion sort is better than the selection sort. In the insertion sort, the number of comparisons are less as compared with the selection sort. So therefore, automatically it gives better efficiency than the selection sort. And in the last class, I said that selection sort is available in different forms. Different forms of selection sort techniques are available. And one of these techniques, little bit by modifying it, we have got insertion sort technique. So therefore, I can say that insertion sort technique is related to somewhat selection sort. But the way the elements are sorted, the way the elements are being kept in the order is different from the selection sort, straight selection sort technique that we have discussed in the last class. And insertion sort is also easy to implement, like the bubble sort and the selection sort. Since the number of comparisons done by the insertion sort for keeping the data in the order is less, so therefore it keeps less load or less work on the CPU. And already I told you that it is giving better efficiency than the selection sort and the bubble sort, because it keeps the data in the order by making use of less number of comparisons as compared with the selection sort technique. Let us see what is the assumptions that we are going to have before we are proceeding to the insertion sort. Already we have discussed in the last two classes that the assumptions are same for all the sorting techniques that we are going to discuss. But anyhow, I am repeating the 5 assumptions which we have made in earlier classes. That is, for sorting the set of numbers, first we are taking an array X. And this array X we are using for storing n elements, where n represents the number of values that we would like to sort. N is the number of elements that are going to be stored in the array X. And since n elements are there, array indexing is starting from 0. So therefore, if you store n elements in the array X, they are occupying the array indexes from 0 to up to n minus 1. Means the last element will be stored in the index position n minus 1 in the array. First element is found at index position 0 and the last element will be available at index position n minus 1. And we are assuming that initially the elements which are stored in the array X are unordered. They are unsorted elements. And using insertion sort, we are going to keep all these elements in the sorted order from smallest element to biggest element. So means elements are arranged in the ascending order. In order to keep the elements in the ascending order, like in earlier passes, here also we are taking several passes through the elements of the array X. A pass means you have already you have known what is a pass. Pass means moving from the first element of the array to the last element of the array is called pass. When we are moving, we start with the first element of the array and we will go up to the last element in the array, in which we are going and touching each element in the array. And during this pass, what we are going to do is we are going to perform certain operations on the elements of the array to bring orderliness among the elements of the array. So these are the 5 assumptions that we have taken in the last 2 classes, and same assumptions we are continuing for insertion sort. And the same thing will also be there for the consecutive sorting techniques that we are going to discuss in our subsequent classes. Now, what is the logic of this insertion sort? Insertion sort logic is very simple, where first the unordered elements we are keeping in the array X. This array X, we are logically dividing it into 2 lists. One list is called sorted list and another list is called unsorted list. Means here we are logically dividing the array X into 2 lists. One is sorted list and another one is unsorted list. Sorted list will be there at the leftmost end of the array and unsorted list will be there at the rightmost end of the array. Means left side we are having sorted list and right side we are having unsorted list in the array. What we are doing with these 2 lists? These are logical division. Logical division among the elements. Initially, we are assuming that x of 0 means the first element of the array is said to be in the sorted list. And x of 1 means the second element to the last element, nth element. X of 1 to x of n minus 1, because the last element is found at the index position n minus 1. So x of 1 to x of n minus 1, these elements are initially said to be in the unsorted list. Means this is the list of elements which are not in the sorted order. So here the second point you should be very clear that we are dividing array X into 2 lists, sorted list and unsorted list. Initially in the sorted list only one element is there, that is first element of the array, that is x of 0 is there in the sorted list, and all other elements means n minus 1 elements from index position 1 to index position up to n minus 1 they are considered as a part of unordered list. So once this division is very clear in the array, then go to the third step. What is done in the third step? In each pass means we are moving from the first element to the last element of the array, which are to be sorted. The elements in the array which are to be sorted. In that elements, we are moving from first element to the last element. Here we are moving in the unsorted list, from the first element of the unsorted list to the last element of the unsorted list. Last element of the unsorted list. So that we are calling it as a pass. In each pass, what we are doing is we are selecting the first element from the unsorted list, and we will keep that element in the proper position in the sorted list. First element means unsorted list is there from the index position 1 to index position n-1. In each pass we will pick up first element from the unsorted list. Means in pass 1, the first element is x of 1, and that x of 1 element we are taking and keeping in the sorted list at its proper position. And then in the second pass, the first element becomes x of 2, and that we are taking from the unsorted list and we are keeping in the sorted list at its proper position. Like that, in each pass we will take first element from the unsorted list, and that element is kept inserted in the sorted list at its appropriate place. Means after every pass, the number of elements in the sorted list will be increased by 1, because in every pass we are inserting one new element into the sorted list, and in every pass we are taking out one element from the unsorted list. So therefore in every pass the number of elements in the unsorted list will be reduced by 1, and the number of elements in the sorted list will be increased by 1. That is how we are doing. Since initially we have divided this array into two lists, sorted list and unsorted list. Sorted list is having only one element. Unsorted list contains n-1 elements. To keep all these n-1 elements into the sorted list, how many passes we have to take? Because in each pass we are taking only one element. But how many elements are there in unsorted list? n-1 elements are there. So we need n-1 passes to pick up all the numbers from the unsorted list and to keep them in the sorted list. So entire algorithm will be having n-1 passes. That is what written here. Step 3 is repeated n-1 times, so that the size of unordered list becomes 0, because unsorted list contains only n-1 elements. In n-1 passes, all these elements are taken out from the unsorted list and they are kept in sorted list. So after n-1 passes, the number of elements in the array becomes 0. So means there is no unsorted list after n-1 passes. After n-1 passes, we are going to have only sorted list with n elements. That is what we are doing. Now let us write the procedure using the loop control variables and other variables required for proceeding in the insertion sort. The procedure for sorting the elements of array X is very simple. The first step is X of 0 is assumed to be the sorted list with one element. That is very clear. And in each pass of I is going to change, because unsorted list is starting from index position 1 and it will end at index position n-1. In each pass we are picking up one element from the unsorted list. That too the first element from the unsorted list. So in each pass of I, where I is changing from index position 1 to index position up to n-1, we are selecting in each pass the first element x of I, and we will keep them in the sorted list, and sorted list will be there in each pass from x of 0 to x of I minus 1. Sorted list will be available. So in ith pass, the sorted list will be x of 0 to x of I minus 1. So we will search the correct position from the elements x of 0 to x of I minus 1. Okay, and when we found a proper position among these elements x of 0 to x of n minus 1, at that position we will insert x of I element. And in order to make a space for x of I element among the elements from x of 0 to x of I minus 1, what we are doing is, see here, to keep x of I at proper position in the sorted list, we will shift all the elements of the sorted list whose values are greater than x of I. Means we are comparing the elements of the sorted list against x of I value. The elements in the sorted list which are greater than x of I, they are shifted to the right by one position, so that you are getting a vacant place. Means all the elements which are larger than the x of I, they are shifted to the right by one position. Okay, so this process repeats until you come across an element in the sorted list which are smaller than x of I, or when you reach the beginning of the list, sorted list, there we will stop the procedure. And at that position, after shifting all these elements, then we will keep x of I in its proper position. Means when ith pass is over, all the elements from x of 0 to x of I will be in the sorted order. That is the thing. And this procedure we are going to repeat n minus 1 times. Same procedure. Step 2 is repeated n minus 1 times, because sorted list should get n minus 1 elements into it. At the beginning it is having only one element x of 0, and the rest of n minus 1 elements are there in the unsorted list. In each pass we are adding only one element into the sorted list. So if you are taking n minus 1 passes through the unsorted list, then all elements of unsorted list will be getting added to the sorted list. So after n minus 1 passes, the number of elements in the sorted list becomes n, and in the unsorted list becomes 0. Means there is no unsorted list. So this is the procedure that we are going to do. And this can be explained with a set of integer values. Here we have taken a set of integer values, 8 integer values we have taken. And these 8 integer values we have arranged from index position 0 to index position 7 in the array x. X of 0 to x of 7. And what are these integer values? Same set of integer values, whatever integer values we have used in the selection sort and bubble sort. Same in set of integer values we have taken. 25, 57, 48, 37, 94, 33, 86, 12. So these are the elements which are not in the sorted order at the beginning. So these elements we are going to keep them in the sorted order by using the techniques of insertion sort. Initially the elements are like this. There is no particular order, and we are dividing this array x into logically 2 separate lists. In the first list, this is the sorted list with only one element, means first element x of 0 is assumed to be the first element in the sorted list initially, and then all n minus 1 elements, means index position x of 1 to up to index position n minus 1. Since here n value is 8, the last index will be n minus 1. N minus 1 means 8 minus 1, it is 7, index position 7. Means x of 1 to x of n minus 1, all other elements, n minus 1 elements are assumed to be in the unsorted list. Means this is the sorted list with one element 25, and all n minus 1 elements are in the unsorted list. In every pass we will pick up first element from the unsorted list. Now let us go with pass 1. In the pass 1, we are taking the first element from the unsorted list. Here, first element in pass 1 is nothing but the element which is there in the index position 1 in the pass 1. Index position 1 means x of 1. X of 1 value is 57. That 57 we are storing initially in pass 1 in the temporary variable t. Now what we have to do? We have to compare this element with the elements in the sorted list. In the sorted list we have only one element, that is 25. So we will compare this element in the sorted list with this value 57. If the elements in the sorted list, if they are bigger than this element t value, if they are bigger than t value, then we will shift that element to the, we will shift the elements of sorted list to the right by one position. But here 25 is not bigger than 57. So therefore no shifting is done. We have compared the element of sorted list. Sorted list contains only one element, that we have compared with the value of the variable t, and this element, sorted list element x of 0 is not greater than t. So therefore no shifting is performed. Means this 57 should be kept at its proper position. This is the proper position. Okay, so there we will insert. Means after pass 1 is over, one element 57 is getting added and they are kept at the position x of 1. Means by the time pass 1 is over, the elements from x of 0 to x of 1 are in the sorted order. Means by the time pass 1 is over, one element is added into the sorted list. Now the number of elements in the sorted list becomes 2. That is, number of elements in the sorted list becomes 2. Initially the number of elements in the sorted list is only 1. By the time pass 1 is over, one element is added, and previously already one more element is there. So 1 plus 1, total 2 elements. The number of elements initially in the unsorted list are 7. And now pass 1 is over, one element is reduced. The number of elements in the sorted list are now only 6. Means by the time pass 1 is over, the number of elements in the sorted list becomes 2. The number of elements in the unsorted list becomes 6. Let us go with pass 2. This is the output of pass 1. And in the pass 2, we pick the first element from the unsorted list. The first element from the unsorted list is now x of 2. X of 2 value is 48. In pass 2, we will take this element, we will store them temporarily in variable t to find out the proper position, because this t value means the 48 should be inserted into the sorted list at its proper position. We have to determine its proper position in the sorted list. For that purpose, we are taking out 48 from here, we are copying that value into variable t, and we will compare this 48 value with all the elements in the sorted list. Now the sorted list contains 2 elements. We have to compare with the 2 elements. And if any element in the sorted list, if it is found to be greater than t value, then we will shift that element to the right side by one position. Now comparison 1 starts with 57. 57, whether it is greater than t value is 48. Yes, 57 is greater than 48. Shift 57 to the, after comparison 1, shift that element to the right side by one position. We have shifted. Now 57 is previously in x of 1 position. Now it is being copied into x of 2 position. So now we have got vacant position after comparison 1 at x of 1 position. Now comparison 2 is done with the second element in the sorted list. The next element in the sorted list is 25. Compare this 25 with the t value. Whether 25 is greater than 48 or not. Whether it is greater than t value or not. It is not greater than. So no shifting is done for 25. Means 48 should be, we have to stop comparison. But fortunately here the number of elements are also over in the sorted list. Now since no shifting is done here, we can identify that the correct position for 48 is only this place. So therefore 48 is inserted here. Now by the time pass 2 is over, the number of elements, previously only 2, the number of elements in the sorted list are 3. And how many comparisons are done in pass 2? In past 2 we have done two comparison. One comparison with 57, another comparison with the element 25. Two comparisons are done in past 2. And the number of elements after past 2 in the sorted list are 3. And the number of elements after past 2 in the unsorted list is only 5. So sorted list contains 3 elements, unsorted list contains 5 elements. Total elements are 8. In past 2 the number of comparisons are 2. Now go with the past 3 and let us see in past 3 what is going to happen. So this is the output. For past 3 the output is past 2. This is the status. Before past 3 is going to start, the number of elements in the sorted list are 3. Number of elements in the unsorted list are 5. Initially sorted list contains 3 elements, unsorted list contains 5 elements. Now in the past 3 we have to take first number from the first element from the unsorted list. The first element for past 3 is the element which is there at index position x of 3. We have to take. X of 3 value is 37. So 37 is copied temporarily into temporary variable t. Now this t value to be compared with all the elements in the sorted list. How many elements are there in the sorted list? 3 elements. Means 3 comparisons are to be done. So first comparison is with the value 57. 57 whether it is greater than t value or not. Yes, it is greater than t value. So therefore shift 57 to right side by 1 position. Previously 57 was there in position x of 2. Now it is shifted to position x of 3. Now the comparison 2 starts with 48. 48 whether it is greater than t value or not. Yes, 48 is greater than 37. 37 is the present t value. So therefore shift 48 to the right side by 1 position. See, this position is vacant. So therefore we are shifting. 48 value shifted from x of 1 to position x of 2. Now third comparison with value 25. 25 whether it is greater than t value? No. It is not greater than t value. So therefore no shifting is done for 25. Means the correct position for 37 is this one. Therefore 37 is copied to this position. Now by the time past 3 is over, the number of elements in the sorted list are 4. The number of elements in the unsorted list are 4. Previously unsorted list contains 5 elements. Now it contains only 4 elements. Previously sorted list contains 3 elements. Now after past 3 is over, sorted list contains 4 elements. Like this, in the fourth pass, we will take the first element from the unsorted list and it should be kept at the proper position. So like that, the same thing can be repeated. I have given the outputs for pass 4, pass 5, pass 6 and pass 7. What is the status of elements after pass 4? So this is the status. After pass 4 is over, the number of elements in the sorted list becomes 5. Number of elements in the unsorted list becomes 33. 3. And in pass 5, what we have to do is, in pass 5, we have to pick up the first element from the unsorted list, that is 33. And it should be kept at a proper position. After pass 5 is over, the number of elements in the sorted list becomes 6, unsorted list becomes 2. And in pass 6, what we have to do? We have to pick up first element from the unsorted list 86. It should be kept its proper position. So by the time pass 6 is over, the number of elements in the sorted list are 7 and unsorted list is only 1. In pass 7, what we have to do is we have to take first element from the unsorted list. Here, since unsorted list contains only 1 element, it is only the first element and it is only the last element. We have taken 12. We have identified proper position for this 12 in the unsorted list and we have inserted at its proper position. Means if you see the number of comparisons in each pass, the number of comparisons in pass 1 becomes 1. And in pass 2, number of comparisons are 2. See here. Number of comparisons in pass 2 are 2. And the number of comparisons in pass 3 are 3. In number of comparisons in past 4, now you know, is 4. The number of comparisons in past 5 is 5. Number of comparisons in the past 6 happens to be 6, but rarely the number of comparisons will decrease, because here it has been decreased. Because you know, when you are comparing, you are going on comparing until you come across a element which is smaller than t value. When you come across a smaller element, the smallest element which is whose value is less than t, then we will stop comparison here. Means in past 6 you have compared the 86 value with 94, and in past 6, for past 6 input is this one. You have to take 86 and you have to keep it in proper position. You have compared 86 value with 94 and you have shifted 94 here. Then we will compare 86 value with 57 and we found that 57 is not greater than 86. So therefore we have stopped our comparison there, and we identify that the 86 should be kept between 57 and 94. So there we have kept only 2 comparisons. There is no need to compare here with all these elements. So sometimes it happens. That's what I told. In the insertion sort compared with the bubble and selection sort, number of comparisons are less as compared with the other 2 sorts, the earlier sorting techniques which we have discussed. The number of comparisons based on the integer values that we are sorting, the number of comparisons, it may not be always same. So the number of comparisons will be decreasing. Actually, in past 6 we are supposed to have 6 comparisons, but here 6 comparisons have not been done. Like that it may be reduced. The number of comparisons may be reduced in different passes. It need not be always in past 6 and past 7. It may also be there in past 1 or past 2 or past 3. It may also happen there. And in each pass also the number of comparisons may be reduced. So that's what I told in the beginning, that insertion sort will be taking less number of comparisons as compared with the bubble sort and the selection sort. But in past 7 the number of comparisons becomes 7. But we will consider a worst case situation where in past 1 comparison, past 2 comparison, past 3 comparison, past 4 comparisons, past 5 comparison, past 6 comparison, past 7 comparisons. Like that, the worst case behavior we will take. And best case behavior is, in each pass we are having only 1 comparison. Means if the elements are already in the sorted order, then in each pass we will be having only 1 comparison. The worst case situation arises when the elements are kept in the decreasing order. When the elements are kept in the descending order, then we will face a worst situation where in past 1 you are having 1 comparison, past 2 comparisons, past 3 comparison, in n-1th pass n-1 comparisons will be there. And in all other cases the number of comparisons will be more than 1 and less than n-1. That is how the average behavior. Now after analyzing all these factors of the comparisons done by the insertion sort, let us try to find out the time complexity of insertion sort. Here, for calculating the time complexity of insertion sort, we consider worst case behavior. That is, in the first pass we are having only 1 comparison, and second pass 2 comparisons, third pass 3 comparisons, like that. In the last n-1th pass n-1 comparisons. So total number of comparisons to sort all elements of the array in the proper order from smallest element to the largest element. The total number of comparisons are required is 1 plus 2 plus 3 plus up to n-1. This is nothing but sum of first n-1 natural numbers. We know the formula for sum of first n-1 natural numbers, isn't it? So what is the formula for sum of first n natural numbers? It is n into n plus 1 by 2. But here we are calculating the sum of first n-1 natural number. So therefore, in that formula, wherever n is there, we replace n with n-1. then we will get a formula like this: n into n minus 1 by 2. If you split the terms, it becomes n square minus n divided by 2. Still, if you split the terms, it becomes half n square minus half n plus 0. Means it is, the equation is in the form of ax square plus bx plus c, where a value equal to 1 by 2, b value equal to minus 1 by 2, and since c term, constant term is there, c value becomes 0. Therefore, it is an equation with order 2. So therefore, the time complexity of this algorithm, by after ignoring the least contributing terms, we can say that the most contributing term is n square. So therefore, the time complexity of this algorithm is order of n square. And space complexity of this algorithm is nothing but, here we are storing n values, n integer values, and each integer, assume that we are working with a 16-bit machine. So therefore, each integer value occupies 2 bytes. For storing n integer values in the array, we need 2n bytes of space. And if you are using any additional variables like the temporary variable t and loop control variables, if you are using in the program like ij, and you can count, suppose 5 variables if you are using in the program, then the space for that 5 variables should also be included in the space complexity. Okay, so here space complexity, since we are using only one array with a storage capacity of n elements, the space required for storing n elements is on a 16-bit machine 2n bytes. And if any additional variables are used, 2n plus that additional terms into 2 should be added. Like that, you can calculate the space complexity. And let us see the pseudocode for this concept. Pseudocode is a generalized code, it makes use of some words in the English. Each word specifies a task to be performed by the computer. And pseudocode here, it is a generalized code. It is not related to any programming language. The advantage with the pseudocode is the statements written in pseudocode can be easily converted into the statements in any programming language. That is the advantage with the pseudocode. Let us see how the pseudocode is written. The procedure here we have written as insertion sort. It is expected to receive 2 arguments from the calling function. The first argument is an array which contains the set of integer values which are to be sorted. And the second argument is the variable n. It specifies the number of elements that are available in the array x. See, here we have defined 3 integer variables I, j, t. I variable we are using to keep track of the number of passes. How many passes we are taking. If I value equal to 1, it is the first pass. I value equal to 2, it is the second pass. I value equal to 3, it is the third pass, like that. And how many passes we need to sort n elements. Already in the example we have discussed. For n elements, we need n minus 1 passes. So I value is going to change from 1 to up to n minus 1. So I is changing from 1 to n minus 1. And in each pass, we are taking the first element from the unsorted list. And we are assuming that x of 0 is assumed to be the element in the sorted list. Means sorted list contains only one element initially. And all other elements, means x of 1 to x of n minus 1, they are assumed to be in the unsorted list. So therefore, I value is starting from 1, because unsorted elements are found from index position 1 up to n minus 1. Now, for each value of I, one element from ith position will be taken and it is kept in its proper position in the sorted order. For ith pass, the sorted lists are available from x of 0 to x of I minus 1. We know that. Now, in each pass, we are taking the first element of the unsorted list, that is x of I value. Temporarily, we are storing in the temporary variable t. And this t value is compared against all the values, because in the ith pass we know that the sorted list is available from I minus 1 down to 0. Means from index position 0 to index position I minus 1. So this is the sorted list for I to pass from index position 0 to index position I minus 1. What we are doing is we are comparing each element in the sorted list from the end of the sorted list, means from I minus 1 position. We are comparing each element with the t value. If any element in the sorted list from sorted list, if it is greater than t value, then we are shifting that element to the right side by 1 position. So initially j value is I minus 1 and j is going to change, going to decrease in each pass from j I minus 1 down to 0. So when j value equal to I minus 1, we are comparing x of j with t. If x of j happens to be greater than t value, then we are shifting x of j to the right side by 1 position, and to that position we are copying x of j. Now x of j position becomes empty. Then in the next pass, this is happens if x of j is greater than t. Suppose if the x of j is not greater than t, immediately we will be coming out of the loop, because x of j is not greater than t means its value is smaller than t. So therefore we are stopping, and the correct position for correct position for the value of t is x of j plus 1 position. We are coming out of that loop and we are copying t value into x of j plus 1 position. Suppose if this is greater than x of j is greater than t, we are shifting, and then we are continuing with the next value of j. Next value of j is I minus 2, and that I minus 2, x of j is compared, j value is I minus 2, means x of I minus 2 is compared against t. If that is greater than t, then we are shifting that to right by 1 position, and j value is a decrement. So this happens until we come across a smaller element. When you come across a smaller element, automatically break statement is executed, you are coming out of the loop, and then at x of j plus 1 position you are inserting that element, and then I value is going to be increased by 1. I value in the first pass it becomes 1, now it becomes 2, means the next element from the unsorted list from x of 2 position is selected, and for that it will identify the correct position. The inner loop will identify the correct position for x of I element and keeps that x of I element in the sorted list. So this is like that I is repeated from 1 to n minus 1, means the outer loop is executed n minus 1 times, and for every value of I, j is going to change from 0 to I minus 1, means we are taking in the reverse order. J is keeping track of the elements in the sorted list from j minus 1 down to up to 0, and always j cannot move up to 0, because when j is coming across an element x of j whose value is smaller than t, there it will stop the comparison, and immediately it inserts that element at x of j plus 1 position. That is how this loop is written, and this program can be converted, these statements can be easily converted into the statements in C language, and using these statements, pseudocode statements, it is possible to you to write algorithm. Algorithm means it contains the statements of English, or it contains English phrases. So each statement of the pseudocode can be easily converted into the statements in English. A step-by-step statements in English written to sort the numbers is nothing but an algorithm for insertion sort. So this is writing algorithm is being given as an exercise to you. You just see the statements of pseudocode, then convert each statement into a statement in English. Step by step procedure you write. So then it becomes a algorithm. And in the examination, you may be asked to write either algorithm or pseudocode or both. Whatever they are asking to write algorithm or pseudocode or both, you write both always. You write pseudocode first and then give algorithm next. Or write algorithm first or then write pseudocode. Writing pseudocode is easier first, and then convert that pseudocode into the algorithmic statements. Now, the code for insertion sort. The code is very simple. Here we are not doing not a great thing because already pseudocode is available. So therefore C functional code can be easily written using pseudocode. Pseudocode is very closer to the statements of the programming language. So therefore, if you are having grip on a programming language, pseudocode you can easily convert into the statements in a programming language. Here we are converting the pseudocode statements of insertion sort into a equivalent statements in C language. Our function name is insertion underscore sort. We have not written the word completely insertion because if we write the complete word, then the number of characters in the function name becomes beyond 8. Most of the C compilers cannot recognize that name. Most of the C compilers are capable of identifying only 8 characters in the function name or variable name or array name. So we have to limit the identifier names to have maximum of 8 characters. So because of that reason, instead of writing insertion, I wrote ins underscore sort, total 8 characters. This is the function name, and its return type is void, means it is expected that it is not returning any value to the calling function. And this function is expected to receive 2 arguments. First argument is an array x, which contains a set of values which are to be sorted, and second argument is n value, integer value, that will represent the number of elements that are available in the array x. Now inside the function we have declared 3 variables I, j, t. I is used as a loop control variable which keeps track of the number of passes through the unsorted list, and j is used to keep track of the elements in the sorted list, and t always holds the value of the first element of the unsorted list in each pass, and this t value to be inserted at a proper position in the sorted list. So sorted list is kept in track by the variable j, and I will be keeping track of unsorted list, and it is picking up first element from the unsorted list for each pass of I. See this. Sorting the elements of the array x. Assume initially x of 0 is in the sorted list with only one element. And unsorted list contains all other elements from index position x of, means index position 1 to n minus 1. Means all the elements from x of 1 to x of n minus 1 are initially assumed to be in the unsorted list. They are assumed to be the part of unsorted list. Now I value is starting from 1 and it will go up to the last unsorted element which is available at index position n minus 1. I is going to change from 1 to n minus 1. For each value of I, we are taking the first element from the unsorted list and this t value to be kept in the sorted list at its proper position. So to keep track of the proper position, we are comparing all the elements in the sorted list against the t value, and whatever elements are bigger than in the sorted list, then the t value, all that elements will be shifted to the right by one position. That is what we are doing in the internal for loop. For j is equal to I minus 1 till we go up to j is greater than or equal to 0. We will proceed up to j is greater than or equal to 0 if and only if x of I is greater than x of j is greater than t. If x of j is greater than t, then only we are shifting that element. Otherwise we do not shift. Immediately this loop is broken. Means if you are coming across any element in the sorted list whose value is not greater than t, then the condition becomes false. 2 conditions must be satisfied to enter into this for loop. Means one is j value should be greater than or equal to 0, and another thing is the element of the sorted list should be always greater than t. Then only this condition becomes true. If any one of this condition fails, the entire condition becomes false and we are not permitted to enter into the loop. There it will stop and it identifies the correct position at j plus 1, the t value is inserted, and then I will be continuing with the next value. That is how we are writing the function. So once this insertion function is ready, then you can make a call to this function by passing the array x and the number of elements in the array as an argument to this function, and this function will sort all these elements. That is how we can write the complete C program. Let us see the complete C program for sorting the set of n values using insertion sort. So already I told in the last classes when we have discussed bubble sort and selection sort, the main program is always same. Only which is going to change, only the function which we are discussing, that function is going to change, and the main program is same. See, this program reads n values from the user and sorts them using insertion sort. The prototype declaration of this function. This function is declared as it is there in the function header. Why? It means it is not returning any value to the calling function, and the function name is insertion underscore sort, and it is receiving two values from the main program. The first argument is array x and second argument is number of elements that are available in the x. The array x contains subset of values. How many values are there in the array x is specified by the second argument. This is called prototype declaration of the function insertion sort. Now in the main program we have declared an array with a capacity of 20 elements, and all that 20 elements it can store is integer type, and n is a normal variable which is used to keep one integer value that specifies the number of integer values available in the array x, and I is used as a loop control variable to keep track of the elements in the array x. Now we are asking the user how many integer values are there. Then user will enter n value. That n value we are instructing the computer to read and store in variable n. N value may be 8, n value may be 5, n value may be 10, n value may be 50. But it should not go beyond 20, because you have array to store maximum 20 integer values. If you are having more number of values, just increase the size of the array and then you can store them in the array. Now for this program, you cannot go for the integer values beyond 20. Integer values beyond 20 means the set of integer values should be kept maximum up to 20. That is how you have to do. Now we are asking the user to enter all that integer values in a row, and we are using for loop from 0 to n minus 0 to up to I will change n minus 1, because I is less than n. I is less than n means I can take up values up to n minus 1. So 0 to n minus 1, all that integer values are stored one by one. They are read and they are kept from x of 0 to x of n minus 1. Then we will display the given elements before sorting the elements. How the elements are stored in the array, so all that we are going to display here. And then after displaying the elements before sorting, then we are making a call to insert sort function. For that we are passing array name x as an argument and number of elements that are available in the array x as an argument. Now once you are making a call to insertion sort function, the main program is suspended temporarily for its execution, and main function program is stopped there, and the control is transferred to the insertion function, and the insertion function receives array x and the number of values available in the array x as an argument. Then the same function we wrote here, it will sort all the elements of the array x and keeps them in the sorted order. And once the sorting is over, then the control comes back to the main program where it was interrupted, where it was stopped, and from that position it goes on executing. Here you have to remember that array name you have passed it as an argument. And in C, we know that array name is acting as a pointer. It point out the address of the first element in the array. Array name X is acting as a pointer, constant pointer to the first element of the array. So therefore you are passing array as an argument to the insertion sort function. Since you are passing array through a pointer as an argument to the called function insertion sort function. So therefore insertion sort function will work with the array used by the main program. Means whatever changes in the element positions are made by the insertion sort function, and all that changes will be reflected in the array of main function. Means indirectly the main program and the calling function, both they work with same set of elements. Means they work with same array. So any changes made to the elements by the called function insertion sort will be reflected in the main program. So therefore insertion sort is keeping all the elements of the array X in the sorted order. So therefore they are displayed here. So here we are displaying the values of the array X. The elements of the array after sorting are, then all elements are displayed. Then the main program will be closed. So this is how you can write the entire C program. This is the starting, and then this is the second page, and this is the third page of your program. So like this, using insertion sort, you can sort the elements. I request all of you to type this program on your computer and see whether this insertion sort is sorting the elements or not. And if you have any doubts, you can call me. And what are the assignment questions related to insertion sort? Only 3 questions. Like in the previous classes, sorting techniques, when we have discussed whatever questions I have given, the similar type of questions. First question is, explain insertion sort with a suitable example. Then you have to explain whatever logic we have discussed for insertion sort. That logic of insertion sort means, what is insertion sort? Means a little notes about insertion sort, and then what are the assumptions before we are going to explain the insertion sort technique. All that 5 assumptions, and then what is the main logic, how it sorts the elements, that main logic, and the procedure step, how it is done by the insertion sort, you have to explain. And after that you have to give an illustration for one pass, how the comparisons are made and how the elements are kept in the order. For one pass you explain the number of comparisons, and for pass 2, pass 3, pass 4, pass 5, pass 6. Okay, like just like this you can give the status of the elements after each pass. And if you wanted to explain for 2 or 3 passes the number of comparisons, how it is done, you are welcome, but it will take time. So therefore explaining for only one pass is enough. And for insertion sort, pass 1 is a small thing, so then you can go with the pass 2 and pass 3 also, there is no problem. But in selection sort and bubble sort, we have discussed that in pass 1 so many comparisons are done in pass 1 itself. But here in pass 1 you have 1 comparison, pass 2 2 comparisons, pass 3 3 comparisons. So therefore you can explain 3 passes for insertion sort, and then for other passes directly give the status of the elements. Then if they are asking to compute the time complexity and space complexity, then you can write this, otherwise there is no need. Up to that, up to this slide, you can explain the insertion sort, that is enough, and there is no need to compute the time and space complexity for insertion sort, unless otherwise it is asked, don't do it. And suppose if it is given for 10 marks question, then you can go with the calculating the time complexities. Then the second assignment question is, write pseudocode and algorithm for insertion sort. Pseudocode already I have given, and I requested you to write the equivalent algorithm using the pseudocode. Simply convert pseudocode statements into the statements in English, and step by step those statements you write, it becomes an algorithm. Then write the C program to sort n integer values using insertion sort. So we discussed how to write the program for sorting n integer values using insertion sort. So that program, 3 slides program, you have to write and explain that program. So this is about the insertion sort. And if you have any doubts in the insertion sort, you can call me on 9848919656 so that we can discuss your doubts in Zoom, or we can discuss your doubts over the phone. Okay, so I will be available to you between 9:30 a.m. and 5 p.m. on all working days. Okay, so thank you for your patience listening. Thank you all.